Hello, everyone, and welcome to this new MLIR Open Meeting. Today we have Dave who's going to talk to us about a nice tool that Dave worked on. Dave?
Yeah, thank you, Mehdi. Hi, everyone. So this is my second talk that I'm giving on MLIR query. I've already done one during the URL VM. I don't have much features that I've added except autocomplete. So this talk will mostly focus on how the current implementation of MLIR query works and try to get some feedback. Okay, so the agenda for today is introduction and some things MLIR query can do, and some examples and how those examples are implemented, and how function extraction works and the implementation, and the review, fabricator review that I've made yesterday, and then if a demo if time permits, and then suggestions or questions. So I've reused the same slide for URL VM. So just to give a quick review and some context on what MLIR query is. So MLIR query is an interactive query tool for MLIR, and it has a REPL interface for querying various properties of MLIR code. You can type in any query you want. And then it can assist in debugging and testing, and it's a standalone tool. So I'll show you what it can. So some capabilities, some things that MLIR query can do. So it can find operations based on certain properties like constant. So in this case, you can, if you have an MLIR query prompt, you can type match isConstant to match all the constant operations. And then you can find useDef up to n steps backward or forward. So for example, you can do match get users of an isConstant up 2 steps backward. You can also extract these matches into a function, a separate function, which you can do with adding a dot extract with the function name. So you have the matcher query, you add a dot extract and then have a function name, and then you get all the matches extracted into a function. So I'll jump straightly into one example query, which is has_op name. So in here we have a basic queries file, a basic queries function, MLIR function, with different operations. We have a hello dialect with different languages. And to load this file, we do MLIR query, basic queries.mlir, then a prompt shows up. And then we can type in the query, match has_op name hello.japanese. So in this case, it matches our operation name hello.japanese, which is this. And we have a match, which is the output of MLIR query. So, but how does it work? So for that, we need matchers. Matchers are the building block for MLIR query. And you can define custom matches that can match almost any pattern. And how this works is that there's a registry class that's responsible for storing and managing matches, which links these matches to which links a matcher string to a function pointer, which I'll show you. And then there's a marshalling layer that wraps these matches with different arguments and infers the arguments and types for use, which is, so this mechanism is inspired from clang-query, which does something very similar. There's a marshalling layer in clang-query as well. This is how the matcher for isConstant op look like. We have a name op matcher, which has a constructor which takes in a string ref as an argument, and then sets it to name. And then we have a match function implemented, which takes in an operation and checks if the operation name is the same as the name with which the struct was constructed. So this struct is made into a function, name op match MOP, which takes in a string ref and returns the class, which returns the struct, the constructed struct. And so once that's done, once we define the matcher in matchers.h, we can add it into the registry. We can simply do register op match, the name of the query you want to link the matcher to. So in this case, which is has op name, links to mop matcher in matchers.h. So we can do something very similar to add. This is already existing. This matcher is already existing in MLIR query, MLIR. So for an isConstant op, it's similar. Match isConstant op matches all the operations that are constants, and it returns a match. And the matcher for isConstant op looks like this. It's the constant op match. It doesn't have a constructor because it doesn't need anything. It just checks if the operation has a trait, a constant-like trait, and then it returns true if the operation has a constant-like trait. So this is how you can define more matches. So new matches that are not already existing in MLIR. You can simply add any pattern you want, and then add a struct with a match operation to add a matcher. So again, to add it into registry, to add it to MLIR query, you can simply add it in the registry with the name isConstant, and then it maps to mConstant, which we just defined here. So now coming to slightly more complicated queries defined by. So let's first go through how defined query works. So defined by has op name test.q. So the test.q has op name test.q should match this, and it looks at the arguments of test.q, and it jumps one step backward, and then those should be the matches that should define test.q. Matches in MLIR query. But the problem is to do something like this with a definitions matches struct, we have to go through each operation. So the definitions matcher will look something like this. We have a constructor with a matcher, inner matcher, which is a matcher itself. And then it looks at all the children of the current operation, and checks if any of them matches the inner matcher. So this is how it would look like. So when you have this query defined by has op name test.q, it goes through each operations to check if the current operation matches it. So it first goes to see so arith constant operation, and gets all its children. So we have get all its uses. We have a test.foo and test.q, and then it checks if if any of the users has an op name test.q. If that's true, it returns true. So in this case, C1I32 returns true because one of the children, which is one of the use, which is test.q, is has an op name test.q. Similarly, these three matches, these three operations also matches the matcher. But this is not very efficient because it looks at all the children and it doesn't save the results anywhere. So what can be a solution to this is memoization to save the matches that are already done, and to pass some extra arguments to store the resulting matches somewhere. So when I had a look at AST matches, which is they use something called, they pass finder and builder into the match function. And we might also need to do something similar to get rid of the inefficiency we have. So let's say if we have we can have a match builder function inside a definitions matcher, which takes in an operation and then also takes in a finder implementation. And then if the inner matcher matches it, we can look at the operands of the current operation and then checks if the defining op and add the defining op to the finder, so that we won't have the problem of going through the same matches twice. But this will need, so for this we will need to change the match function to pass in some new arguments. And the registry is still the same, it doesn't change much. So I'll get into so for the query get all definitions, this is a query which gets all the definitions of an op. So if you have test.useCoo operation, it gets all the definitions up to 2 steps backward. It goes 2 steps behind and gets all the list of all operations. So in this case, we have these matches for test.co, 2 steps back, and we have 4 matches. So I am showing this just to show you how extract function works. So once you have all those matches, you can simply add a dot extract with a test string, so that you get a func.func test and a new function. And how does it work? How does this work? So it works in the following fashion. Once you have all the matches and adds into a func.func, and then after that, it looks at the last operation and adds a return statement with the result of the last operation. And then for the function arguments, it takes all the arguments of our matched operations and then tries to add it to the test. But the problem here is after it adds all the arguments to the test arguments, we see that these functions are redefined. C1, CR1, I32, %0, %4 are redefined. So we need to remove all those extra arguments from the function arguments. So we can simply check the uses. If the function arguments are not used, we simply remove them, since this is redefined inside the function itself. So then we can get a list of arguments that are needed for the function to exist without all the extra arguments. So yeah, I think this was a very short presentation. I opened an initial review, fabricator review, and for that, parser and diagnostics were taking up a huge chunk of the diff. And that won't be changing much since the parser and diagnostics will almost remain the same. The things that might change are the matches, which I didn't want to change now because it might break, since it's already existing in MLIR, it might also break other things if I try to change it, so I didn't touch matches. And I think more changes to the matches can come at a later stage. Yeah, and that's it. Yeah, that's it. If you have any
Thank you
questions, feel.
for the presentation, and thank you for sending the patch upstream. Is there anyone online who wants to ask some question? Feel free to ask in the chat or unmute yourself.
Hi, I'll perhaps sort of like as start us off. So on slide 44, you mentioned only the last one is returned. Could you, I think, elaborate a little bit on that?
On slide?
44.
Sorry, 44. Okay.
So I mean, year only 2 is returned, right?
Oops. Only 2 is returned, yeah.
So I mean, in this case, that works, right? Because you have a, well, actually, I don't even know if that's true, if it works or not. So it is, in a way, like, why return any? And if you return any, why not return more?
Okay, yeah. So this was just done for the sake of having a return statement. So yeah, if we want to return all the operations, we can do that. But I'm not sure how the user would want the function to be. So usually it's the last operation that's returned, right?
Yes, I think the return often here is to avoid, let's say we're extracting a pattern and most of these ops are actually pure. And then so, like the first pass you run may actually just delete the entire function if you don't return, well, not return, delete the function, but delete the body if everything is pure and nothing is actually returning anything. So, I mean, I think with respect to like, I mean, I definitely agree, like things that are actually defined internally, shouldn't be arguments because that's where they're defined. But for returns, I somehow feel like it could depend on the application, but I would assume for a lot of the cases when we want to do extract, it is to verify a pass over this extracted group or a pattern over the extracted group. And so in which case, basically keeping everything live to avoid, accidentally like DCEing them seems useful. So instead of just returning like the last one, returning anything that is not used inside the function itself, that would not be live if not returned.
How do you, so I have a few questions though. How do you match something that is not used in the first place? And also like the extraction, I think is anchored originally to one original op that will be replaced by the function, isn't it? In which case there is like some sort of SSA value to replace that has to be returned by a new call. Unless when you do the extraction, you don't have a replacement.
So I think the extraction is in a way for extracting a sub pattern into a graph, so that there is no replacement.
Okay, I thought there was like an outlining when we do the extraction.
No, it's just extracting the matches into the function. It's not rewriting anything.
Okay. So it's mostly used for visualization then?
Yeah, and testing, extracting test cases, maybe. For, let's say you have a new dialect, then maybe if you need to extract a test case with a certain new operation you made, this can be useful, I
I
think.
I wonder if we don't already have an outlining helper function, and if not, that could be useful actually. You know, to take a slice or to take a list of op from function and implement an outlining, and then the query could just like exercise the utility.
Yeah. Mm-hmm. Yeah.
That's actually good.
That can be moved somewhere inside MLIR, I think.
That was my other question, which is like, how would you, because this seems to be all about the SSA use dev chains, the way we do matching. Do we have other way to do matching?
Yeah, so I did look at PDL, and so I think it wouldn't be very straightforward to have PDLL convert MLIR query to PDLL,
Okay.
because it might need some changes to the PDLL itself, because PDLL, you always need to rewrite something, right? If I'm not wrong. So then you might have to rewrite PDLL to also return the matches instead of simply rewriting. And then even after that, we still need to define, we still need to map these matches to the PDLL matches somewhere. We still need to define a PDLL matcher instead of, yeah, maybe that's the way to do this. I'm not sure.
I didn't think about PDL, but that's a very good point. Consolidating on PDL would be a good idea.
Yeah, I mean, I sort of see this as having, so I mean, a couple of different functions, right? We have current matchers upstream, like mConstant being one of them, and a couple of the other ones that, you know, folks use in terms of like writing people optimizations, you know, like matching the structure. And so in a way, this is a tool to sort of like interactively explore constructing such a matcher. You know, so it's, I mean, not to say like the PDL angle. I mean, I do like that one as well. But I think for me, one of the interesting things here is just the ability. I mean, like the same thing you do with clang-query. If you're matching the AST, you often will fire up clang-query and start iteratively expanding your pattern until you actually get your match. And I sort of see this in a similar vein around those.
There is no one-to-one to PDLL. Like if you wanted matchers, you wouldn't like also be able to map them to PDLL and test them the same way.
I mean, that's a good question. It really depends. Are you actually writing a C++ function of matchers or not? I mean, if executionally, I think that we may be saying different things, but I think executionally, you could probably use PDL to drive a lot of these things. You know, but you're right. Like I'm thinking more of like if I'm offering it, but you're right. Like the offering versus how it's executed are different things.
Just coming back to my previous question, because I didn't think really about that. If I match, for example, a free pointer, can I get all the operation that touches this pointer? Can I,
If you match,
can I walk a block, for example, and say any operation that has a side effect in this block, or this kind of thing?
so you need to get all the matches that has a side effect.
Yeah,
I'm
but
sorry,
not walking the SSA graph, walking the control flow graph.
Mm-hmm.
And I was just not sure how you do that.
Yeah, so I think there are equivalents in like if we look at the clang-query side for these, they get a little bit, you know, more complicated. But you know, there is a, I mean, it's been a couple of years since I've used a lot, but there is a collect all matches kind of thing which allows you to, like in this case, it's probably like match an op, match a region within it that matches XYZ, and then collect all matches inside of that. So
Okay.
it would be a combination of a couple of atoms, I think, or it could be expressed as such.
The reason why I thought about this was you mentioned earlier, Jacques, that we could end up with a function with unused operations, and I was trying to figure out how do we get to such a state actually. But I guess we can also match parents and users before we do the extraction.
Match operands and
I don't know actually.
yeah. So the thing is, when you extract a match, let's say you get a match that's either not used by any of the other matches. So when you extract this into a function, that arith.constant will not be used anymore.
And in this case, what do you do?
So in this case, we just extract it to a function. It doesn't go through all the MLIR opt, so it doesn't do dead code elimination. It will still be there. So there will be C2 I32 arith constant.
It won't be returned, right?
No, not currently.
So tell me again, how is it selected? It's part of the match. So how do you compute? Let's take it differently. How do you compute the return? We just take the last op.
Yeah, that's what I did currently. Yeah, maybe I should change it. Okay. Hello?
Yes, oh, sure. Oh, another question. How does it work if I match across the CFG?
Cross the CFG?
Yeah. I know I have a diamond block and I'm in one of the branch and I match SSS subgraph that goes into the parent block or the predecessor block, terminator block.
I haven't used is there something like I didn't really understand how does that work?
Well, you have a first block, and then at the end of the block, you have a branch that goes, left and right. And then you have another block, and this block can use SSA value from the other block because the first block is dominating the second one. And so you can match and be across blocks, which may not be a problem because if you work the SSA graph, you can always. I was trying to figure out if we would need to extract at some point multiple blocks, but I guess not because you don't have the ability to walk through block arguments. Anyway,
I think that's a good question. I think for extract there is, there's a lot more variance. I think when it's restricted to like these pure use defs, I think we're in a simpler world than once we start being able to extract arbitrary matches in regions. Yeah, in a way, this is just like extracting a little DAG from the graph and popping in a new function. But yeah, you're right. Like once we have ops of control flow and regions that have to be included in this, well, can't say you're right, but I could see that we may need to think about this a bit more. What variance to imply there.
Okay. Yeah, maybe. Yeah. And maybe I'll try to come up with some examples and see if it works still.
And so currently the way to add is relatively simple. You have one register method, a string name, a matcher. So you mentioned for capturing the for caching SFX, additional parts may be needed. Is this something that you see being changed to the regular matchers, or is it something where that means that we need some wrappers for like the query tool to do the caching? Because I'm assuming like this. Well, perhaps it's a question. Does this caching also help in the plain specified cases, or is this something that is that you would only see expected to be used in like the tool?
No, I think it can be useful for normal matches as well. So if you look at this, for instance, so we have something similar. We have something similar to get definitions matcher, which something that does a recursive a matcher in already existing in MLIR matches. So I think if we pass saved list of matched operations, I think it would also speed up the recursive matches that we already have. So in clang-query, they already, for all the matches, they already pass a finder and builder, which does something similar.
Sounds good.
Okay, anyone else online would want to ask a question? Otherwise, I'm gonna thank Dev again for this talk today and for the contribution. Looking forward to it. And we'll see everyone next time.